Hello, my name is Jerry Machado and I'm answering the questions interview of week 5 about recursion. Recursion is a powerful technique for solving problems that can be broken into smaller, self-similar subproblems, often leading to very elegant and readable code. However, it definitely comes with trade-offs. Two of the most significant pitfalls are the risk of Stack Overflow error and the potential performance inefficiency. The first major pitfall is Stack Overflow. Every time a function is called, a new frame is added to the call stack to store its local variable and state. With deep recursion, for example, calculating the factorial of a very large number, you can exhaust the limited stack memory, causing the program to crash. The more reliable way to overcome this is to convert the algorithm to an iterative solution. By using a loop, like a for or while loop, you manage the state manually using variables, which uses a constant amount of stack space. For instance, a factorial can be easily calculated with a simple for loop, which is safe for any large number. In some languages, another technique is tail call optimization. If the recursive call is the absolute last operation in the function, a smart compiler can reuse the current stack frame, effectively turning the recursion into an efficient loop under the hood and preventing a stack overflow. The second common pitfall is severe performance degradation due to recomputing the same values over and over. The classic example of this is a naive recursive function for the Fibonacci sequence. To calculate fib5, for example, you calculate fib4 and fib3. But the fib4 calculation also calculates fib3, leading to a redundant work that grows exponentially. The primary way to solve this while keeping the recursive structure is memoization. This is a caching technique where you store the result of each computation, typically in a dictionary or an array. Before computing, you check if the result for a given input already exists in your cache. If it does, you return it instantly, avoiding the expensive recomputation. Alternatively, like before, an iterative bottom-up approach is often the most performant solution. You can calculate the Fibonacci sequence in linear time by starting at the beginning and working your way up. So, to summarize, the two main dangers are stack overflows from deep recursion and inefficiency from redundant calculations. We solve this by converting the problem to a more memory-safe iterative solution, or we can augment the recursion itself with powerful techniques like memoization to eliminate repeated work and, where possible, rely on tail call optimization. Ultimately, it comes down to choosing the right tool for the job by understanding whether recursion's clarity is worth the potential cost for a specific problem. So thank you very much.